Right, go ahead. Thank you.
Okay, yeah. Thanks for having me. Today, I'm going to share about a very exciting journey that we are exploring that we call fuzzy sphere regularization of 3D conformal field series. And since it's a short talk, I will mostly focus on one of our most recent results on applying this to study the SO5 deconfined differentiations. So the results is contained in this paper, and if you are interested in like the entire journey that we had so far, you are encouraged to check all those papers that we have posted on arXiv. So let me first thank my collaborators on this paper. So Zhen Zhou, who is my PhD student, he's the true hero of this paper, who did most numerical and analytical analysis. And also Wei Zhu, who is a professor at Westlake University, and Liangdong Hu, who is a student of Wei. And they are the key players for the entire journey of this fuzzy sphere regularization of CFTS. Okay, let me first start with a very brief introduction about deconfined differentiations. I guess many of you in the audience are pretty familiar with this concept, in particularly given that all the authors in the seminal papers about deconfined differentiations actually in this ultra quantum matter collaboration. And this transition is an example of phase transitions that beyond Landau's spontaneous symmetry breaking paradigm. It's a transition between a null state that breaks spin rotation but preserves lattice symmetry, and a valence bound solid that preserves spin rotation but breaks the lattice transitions. And it was realized that this transition can be described by gauge series by using critical bosons and U1 gauge field. And after this proposal, there are a lot of very exciting developments on the deconfined differentiations. One of the most remarkable discoveries is that indeed this transition seems to have an emergent SO5 symmetry rather than the SU2 times U1 of the Lagrangian that I showed in the previous slides. And physically, there's a very simple way to understand what does this SO5 symmetry correspond to, right? So remember, it's a transition between a null state and a valence bound solid, where I can have 3-component order parameter of null state and 2-component order parameter of valence bound solid. So in total, I get 5-component. And this SO5 symmetry just refers to the rotation between those 5-component order parameters. And you can write down nonlinear signal models on the target space S4 to characterize this SO5 deconfined differentiations. And a key ingredient is that there's a Western-Lewitton term whose physics meaning is to incorporate the anomaly of these phase transitions, and physically it corresponds to the intertwinement between this magnetic order and the valence bound solid order. Okay, and the theoretical picture for this deconfined phase transition is pretty nice, but there's a very important issue regarding the IR fate of these phase transitions. More precisely, whether this phase transition is a continuous phase transition or first order phase transitions. After decades, 2 decades of study, this issue still has not been completely settled down. There are the major discoveries, numerical discoveries. Firstly, there's no conventional sign of the first order phase transitions that makes people to think maybe it's likely to be a continuous transitions. But if you really want to analyze it using the language of continuous phase transitions, you would then observe some violations of fine size scaling. For example, different approaches give you different results of critical exponents, and you will also see critical exponents are drifting with system size. This is a plot that I got from this remarkable paper, where you can see that this critical exponent called nu keep on drifting, changing as I increase the system size. It's not, it is not stable. Even they are simulating the system up to like L equal to 500, right? And more importantly, it was found that the critical exponents from all those lattice simulations are violating the rigorous bound of the so-called conformal bootstrap computation from conformal bootstrap, right? So this also put a question mark on whether it is really a continuous phase translations. So there are a number of possible scenarios that could potentially reconcile these tensions. For example, it could be a continuous transitions without emergent conformal symmetry, right? So then those conformal bootstrap bounds will not apply. It could also be the case that is really a conformal phase transitions with some abnormal scaling behaviors, either due to some mechanism that we don't understand, or it's just because the universe is making fun of us. So, and the most compelling scenario is the so-called pseudo-criticality or complex fixed points proposed in these papers. And this scenario, there are various ways to understand this scenario. The approach that I would take is to think about a special type of larger generalization of this SO5 nonlinear signal model formulation for the deconfined phase transitions. So as I said, you can, for deconfined phase transitions, you can consider a nonlinear signal model on a target space S4, and that is SO5 quotient SO4, or a Grassmannian that is SP2 quotient SP1 times SP1, right? So now using this Grassmannian language, you can generalize it to a larger inversion that is an SP2 and Grassmannian written like this. So, it is conjectured that for such Grassmannian, it can potentially due to some critical gauge series that has 2n Dirac fermions coupled with the SU2 gauge field. So for this gauge theory, and we can have a better understanding about the general picture of this family of theory. So for example, if the flavor number, this n is large, then we know that the phase diagram, as you tune the coupling strengths of the nonlinear signal models, will look like this. At very small coupling, we will have a spontaneous symmetry breaking fixed point whose ground state just lives on this Grassmannian manifold. But as you increase the coupling to a very strong order 1 coupling, you may disorder the system and end up with a conformal fixed point that we call C here. And this conformal fixed point is conjectured to be described by this critical gauge series with SU2 gauge field. And in between, you will get an order disorder transition, which is also conformal fixed point, but it's a repulsive fixed point. So, and this is a picture that should be correct when n is very large. And now, if you decrease the value of n, then those two fixed point, those two conformal fixed point will approach to each other, and eventually, at some critical value, they will merge at some critical value of n, and then those two fixed points will merge into one fixed point. And with RG flow, looks like this. It's attractive in one direction, but repulsive in the other direction. And what's interesting is that if you further increase the, if you further decrease the value of n, then it will, what will happen is those two fixed points will split again, but this time they're no longer staying in the real axis, but they will stay in the complex space of your coupling constant, and this fixed point is called a complex fixed point. And if n is smaller than nc but very close to nc, what will happen is those complex fixed points will be very close to your real axis, and then the RG flow of your system will walk through around the vicinity of this complex fixed point, give you some behaviors that is very close to the true conformal fixed point that is called a pseudo-critical. And it is so it is conjectured that such scenario of this fixed point collision and complex fixed point and walking behaviors are very generic scenarios for many different types of theories, including various of gauge theories. And in 2+1, in 1+1D or 2D classical system, the best known example are the Q-state pulse models. And in different literatures, it has different names like pseudo-criticality, like complex fixed point, and also like conformality lost. Okay, so then the conjecture for the SO5 deconfined factorization is that it belongs to this scenario that it's not a true critical point, but there are complex fixed points are very close by, such that the RG flow is just slow and the system behaves like critical system. However, so this is the most compelling and scenario to reconcile all the tensions, but it's really hard to find any concrete supporting evidence to directly demonstrate this, because there are several challenges built in to study pseudo-criticality. As you know, the primary tool to study critical systems, 2+1D, are mostly like Monte Carlo simulations of lattice models. But for using this approach, it's very difficult to diagnose emergent conformal symmetry. But to really expose the conformal symmetry, you have to study a conformally flat manifold, like sphere or infinite space. But none of those is available for lattice models. And lattice model have to deal with the system with boundaries, or on a torus, which is not a conformally flat manifold. And also, when you want to extract critical exponents, the lattice model approach would heavily rely on fine size scalings. But for pseudo-criticality or for some other systems, you may have. So for deconfined factorization, there were already like some abnormal fine size scaling behavior has been observed. So that makes extracting critical exponents also pretty tricky. And for the pseudo-criticality and the true critical points, they have very similar behaviors. So if you just measure numbers regarding the critical properties, it's very hard to distinguish those two systems. Okay, but what come to rescue is really this we call the fuzzy sphere regularization. And one punchline for this type of regularization is that it realizes the 2+1D phase transitions on the S2 times R geometry, which is a conformally flat manifold. And more importantly, on this geometry, what we will get is this. What we can get is this so-called radial quantization of the CFT, or is also called the state operator correspondence of CFT. So the statement is that it's a statement. So this radial quantization is valid for any CFTs in any dimensions. So the statement is the following: if you consider a quantum version of the CFT and you put your quantum Hamiltonian defined on a sphere geometry that is SD to the -1. And then the eigenstate of that quantum Hamiltonian will be one-to-one correspondence to the scaling operators of the CFTs. And in particular, the energy gaps of those excited states will be just proportional to the scaling dimensions of the scaling operators up to some non-universal constant that comes from the upstream normalization of the Hamiltonian. And this really gives you a direct access to a wealth of information. For example, you can directly observe emergent conformal symmetry by just checking whether you get integer space levels between primary and descendants. And from the energy gaps, you can also get scaling dimensions of the primary operators. And but unfortunately, this radial quantization in the past only works for 2D CFT, that is 1 plus 1D CFT, because there you just need to put your quantum Hamiltonian on a circle. But for higher dimensional CFT, you need to put a quantum Hamiltonian on a sphere, for example, 2 sphere. But we know that a regular lattice won't fit 2 sphere because 2 sphere has a curvature, right? And what really and the recipe to make it work is that instead of discretizing a sphere, what we are going to consider is to fuzzify a sphere. So in a formal words, we are considering the fuzzy sphere, or also called a non-commutative sphere, which was originally proposed by Mado a few decades ago. But to condense matter, friends, that's nothing but you consider the physics on the lowest number level of a sphere. So eventually you get a fuzzy sphere. So this is also what we are going to do. So let me first give you the model that we are going to study for this SO5 deconfined factorization. So, and this is a version for this large N generalizations that I talked about in a few slides before. So it realizes nonlinear second model with Westerstrom-Norton term on this Grassmannian target space. And the way to realize it is that we consider 2n flavor of fermions on a sphere, and then we put a magnetic monopoles in the center of the sphere. So the Hamiltonian will contain 2 terms. One is just the conventional kinetic term that eventually gives me lambda levels on the sphere. And the other term is an interaction term, as a density-density interactions, which you can think as an analog of Haber model on a lattice. So this density-density interactions contains 2 terms. The first term is really a density-density interaction that where the density is an SU for an invariant density. And so this term is literally an on-site or contact Haber term. And the second term is a pairing interactions, where the pairing term looks like this form. And for people who are familiar with the symplectic group could quickly realize that this pairing term is an SP2N invariant term. So then without this pairing term, we will have a model with SU4N symmetry. But this pairing term just breaks the symmetry down to the SP2N symmetries, which is the global symmetries of this SP2N Grassmannian. And for n equals to 1, that's really just SO5 deconfined factorizations. And we consider a limit that the kinetic energy is much larger than the interaction, and such that I can just study the physics on the lowest lambda levels. And I consider the case that I have filled the lowest lambda level corresponding to that for each orbital on average, I will have 2n flavors of fermions, and for n equals 1, that's just 2 fermions per orbital. Okay, so this is a technical slide, just show that why in the end we end up with this SP2N Grassmannian Western monoid models, but I don't have time to explain this. So if you want to know details, you can ask me later. Okay, so now we can project this model into the onto the fuzzy sphere in the limit that the kinetic energy is much larger than interaction strength. Then I can just safely project the model into a lowest lambda level. And lowest lambda level, the wave function of the lowest lambda level will have this form, which is a monoble harmonics. And the projection is very straightforward, that you just replace the fermion creation operator with a second quantized operators that we call C, and times this spherical harmonics. And it's easy to understand why in the end you end up with a fuzzy sphere, meaning that the coordinates of the sphere are not commuting after this projection. Instead, they follow this SO3 algebra. So indeed, this type of quantum geometry, non-commutative geometry, also has been considered in various different contexts in physics. And so the key for the non-commutative geometry is that the space are not commuting. So in some sense, that's a version of ultra quantum, because the space or geometry is also quantum. And for condensed matter physics, that's really just the physics on the lowest standard level that we are dealing with. Okay, let me quickly mention in the end, we will end up with a model defined on this lambda orbitals, which you can pictorially consider it as 2s plus 1 site fermionic chains. And the interactions that we'll have are just like 4 fermion interactions, which are all-to-all in the orbital space. And the interaction form is called Haldane pseudopotential. And here, the number of orbitals plays the role of the space volume. So the number of orbitals is 2s plus 1. S is a monople flux, and it will play the role of space volume. So in the UV model, we have a number of symmetries, like SPN flavor symmetries, like SO3 sphere rotation symmetries, and as well as particle symmetries. They can be mapped to, they correspond to the IR symmetries, either flavor symmetries or Lorentz symmetries, or the space-time parity symmetries. Okay, so then we just have this model. What we can do is that we can just solve it numerically to say whether we do get conformal symmetries and what's the nature of this n=1 deconfined visualizations. So I don't have time. I think I'm almost running out of time. So, but let me quickly mention that a digression regarding applying this to the 3D Ising transitions, which can serve as a benchmark to demonstrate how good results is. So we really, so using this approach, we can really compute everything you could ever imagine for 3-dimensional CFTs, in particular for 3D Ising. We can demonstrate the conformal symmetries, we can determine the scaling dimensions, OP coefficients, and we can also study conformal defects and so on. And typically what we need to do is that just diagonalize the Hamptonian using, for example, executive diagonalization, then we get spectrum like this. So as I said, we do get the state operator correspondence, which means all the energy gaps will be proportional to the scaling dimensions of my scaling operators in the CFT. So then up to a non-universal factor, we can get this non-universal factor by finding that, for example, the energy moment tensor, we rescale it to 3, and then the rest numbers will just be the scaling dimensions of my CFTs. And then from this, we can say the conformal symmetries, for example, like this integer space, the values of scaling dimensions and so on, right? And from this, we can get a very accurate critical correspondence of primary operators on a ridiculously small system size, like 4x4 lattice or even 2x2 lattice, that we find highly accurate results. So I don't have time to demonstrate those. So, but let me back to this SO5 deconfined differentiation story. So the first thing that we want to, again, what we did is just like what I showed for Ising, that we diagonalize the Hamiltonian on a very small system size and say whether I get conformal symmetry there. So, so as you can see in this phase diagram, what we need to look at is a large V over U region, or the one V over U region, where we will, in the region of conformal fixed point, and then so then you can say that indeed for a very vast region, we do get approximate conformal symmetry. For example, we get an almost conserved energy momentum tensor. We get an almost integer space values between the primaries and their descendants, as well as the descendants of the SO5 conserved current. All the results here now I'm showing is for the SO5 deconfined differentiation. And we can also check the conformal algebra by looking at, if I have a primary, whether I get the integer space descendants from it, and you can say that it's also agrees pretty well, given that it's on a super small system size. And here, and not just for few line states, indeed, we checked like lowest 100 states. We find that all of them seem to form the safety states with no external state or missing state. And among them, we have identified like 19 primaries and 82 descendants. That's really a remarkable number if you have some experience regarding the numerical study of conformal field series. Okay, so and an important question is that for this approximate conformal symmetry, whether it corresponds to that I have a true critical point, or I have a pseudo-critical point or complex fixed point where where I can all have approximate conformal symmetry on an intermediate length scale. So to answer this question, the key is to look at the RG flow of the singlet, the lowest singlet of the system, where, so here is a plot as I vary the system size and also this coupling strength. What you can see is that for given coupling strengths, you will see that as I increase the system size, the scaling dimension of the singlet just keep on decreasing. And in particular, we can say in a vast region that it decreased from slightly irrelevant to slightly relevant. So such RG flow will not happen for the case that you have true conformal fixed point, because it would either always stay in irrelevant, or it will flow from relevant to irrelevant, but you won't say this kind of flow. But for pseudo-criticality, you would exactly expect such RG flow, because if you just look at this flow, it will first be attractive. That means the singlet will be irrelevant, but after it gets attracted to the vicinity of the complex fixed point, it will become slightly relevant and eventually flows away. So this RG flow, this results shown here is a smoking gun demonstration that we indeed, it corresponding to the pseudo-criticality. The SO5 deconfined differentiation correspond to pseudo-criticality, or in other words, the complex fixed points. We can also get a number of primary operators that some of which have interesting physical meanings, but I don't have time to expand those. But let me mention that there are two remaining tasks we need to do in order to settle down the SO5 deconfined visualization. One is that we do want to determine the critical NC for which at which those two fixed points collides, and we also want to identify the complex fixed points for n equals 1, right? All those two things are feasible using the fuzzy sphere regularizations. So there are, of course, a lot to explore in this fuzzy sphere world, but I don't have time to elaborate them. But so let me just wrap up. So the idea is that we propose a new scheme that we call fuzzy sphere regularization to study 3D CFTs by making use of quantum Hall physics. It works miraculously good for a very small system size if we do some fine tuning, and for 3D Ising CFT and also for the SO5 deconfined visualizations. And for SO5 deconfined visualization, we demonstrate the emergent conformal symmetry, as well as we find that the RG flow is signifying the pseudo-criticality caused by the complex fixed point. Okay, thank you.
Thank you very much, Yin-Chen, for a very interesting talk. We're just out of time, but maybe I'll see if there are any quick 1 or 2 questions before I turn off the recording and then open up the free discussion time. I think there was a question of Nati Sabric in the chat, but I think they got resolved. So if anyone else has a question, feel free to speak up. Maybe Dam? Is it Dam-san? Did you unmute yourself?
Yeah. Can I ask you about the 2 problems that you want to determining NC, critical NC, and complex fixed point? So if the critical NC is not an integer, is it possible actually to determine it?
Yeah, that's a, should I answer this question first? Or
you just want to see what value of n the system start to become conformal?
Yeah, so in principle, we can also determine the fractional NC. So, but you know, I don't know the physical meaning of fractional NC. You can think it as one of the one of several ways of an ideal continuum, the model to fractional n. But practically, there's for one type of continuation, we can study it using determinant Monte Carlo. Now, eventually in determinant Monte Carlo, the n just comes as a power of the determinant, which we are free to take it as a fractional value. So for that type of an ideal continuation, we can really determine what's the precise value for the NC. But it may or may not have a physical meaning in the end. But we can certainly know for which integer it's conformal and for which integer it's not. That's some question we can certainly know.
And similarly, is there a sense in which the complex fixed point can be made exact, a notion that's exact? Yeah.
So what we can do is to study a non-unitary Hamiltonian. So then in principle, we can hit this complex fixed point. So this is doable for using fuzzy sphere. But the challenge is really, how do I know I really hit the complex fixed point exactly? Right, that is something pretty subtle. We haven't found a very good way to identify that.
Thank you.
Thank you. And then maybe as a last question, Nati, go ahead.
Well, first of all, thank you for the fascinating talk. And one sign that it's fascinating is that I have tons and tons of questions, but I don't think Ruben is going to allow me to ask all of them. So let me ask one of them. Following up on Damson's question, imagine you found a Hamiltonian which is not Hermitian, and you found this pseudo-critical point, and it satisfies all the things you want. It has conformal symmetry and SO5, etc., etc. The distance from in this picture that is on the screen now between this red dot and the black line is not universal. And I thought that the whole point about this pseudo-critical point is that there is a nearby underscoring nearby critical point. In what sense is it nearby? Is that universal, or what is the distance from the real line from the between the red dot and the real line? Is it meaningful or not?
I think it's meaningful. You can think it as, for example, you just have a phase transition such as Ising transition, right? So, and experimentally or numerically, you are not able to exactly hit the critical point, right? There are always some off, right? And such off critical systems also follow universal behaviors, which will be characterized by how far it is away from the true critical point, right? You do get like critical exponent, collision length exponent, and so on. And from this, you can start to understand the universal behaviors. I think the similar logic also applies here, but no one has really tried to do it very seriously at the moment.
But this logic is circular. You assume that you are nearby, and then you derive results. But is there a sense in
numerically we can, I mean, for this system, we can, if we really find a complex fixed point, then we can see how far it is away from the critical point, right?
Will this be the same with other? If I view the black line as coming from the lattice model, will the distance be the same or not? Because I could have another the black line could be another lattice model, and I might not be nearby.
I think that there might be a canonical way to define the distance, where starting from the fixed point, then you just characterize everything of that fixed point using language of conformal field series, right? And then the distance can be characterized by you deform this fixed point with the singlet, which has a canonical definition, the singlet primary operator, which has a canonical definition, and then with some strengths, right? The strengths then will have the canonical definition, right? Of course, you need some translation between this canonical definition to the lattice models, but this translation will be just have one free parameters, which you can fix eventually. Does this answer your question?
Sort of. I'll have to think about that, but since I hold the microphone, I'll use it to ask another question, unless Ruben shuts me off.
No, actually, you're very welcome to. Maybe I'll just now, I'll end the official part of the talk. I'll stop the recording, but then whoever's interested can stick around for a free talk.